Algebra 2, Simultaneous Equations, Type 2, 3 variables. So in the previous video we saw that we can solve simultaneous equations when we have two variables, and this represented the point of intersection of two lines. When we're looking at three variables, they tend to often be x, y and z, and this is representing the point of intersection of three planes. So using GeoGebra we can see here that three variables is going to represent the 3D plane. So this is our x-axis, this is our y-axis, and this is our z-axis. So for instance, we could be asked to solve for x, y and z, and given three equations, 2x plus y plus 4z equals 23, 5x plus y plus 2z equals 19, and 3x minus 2y plus z equals 13. So let's look at what each of these equations represent first. So our first one is 2x plus y plus 4z equals 23. So we can see the blue shaded area is the plane that is represented by this equation. The second equation is represented by the plane 5x plus y plus 2z equals 19. So this can be seen in the yellow shaded plane. And the third one, 3x minus 2y plus z equals 13, can be seen represented here as the red shaded plane. So what we want to do is solve for where do all three of these planes intersect. And if they all intersect at one point, then we will get one solution for x, y and z. If the three planes did not intersect, we would not be able to find a solution. So for the scope of the Leaving Cert, we will always get one answer for x, one answer for y and one answer for z. So the first thing we want to do is make sure that all of the letters that we're looking for, so all of the variables are on the left-hand side, and all of the constants are on the right-hand side. So in other words, we're going to bring all the x, y's and z's to the left and all the numbers to the right. And in this example, that is already the case, so we don't have to do any rearranging. The second thing we want to do then is to number each of the equations 1, 2 and 3. So this makes it easier for us to go back over our work and to write down exactly what we're doing. Our next step then is to decide which variable it is that we want to eliminate first. So in all three equations here we have x, y and z, so that means it doesn't really matter which one we decide to eliminate. We could choose x, we could choose y, or we could choose z. So I'm going to choose the y's to eliminate first, which means I'm going to take two equations at a time. So I'm going to start with equation 1 and equation 2. And what I can see here is if I look at the y's, I need to make their coefficients the same, but opposite in sign. Now, at the moment, their coefficients are already the same. They're both 1, but I need one of them to be a negative. So I'm going to take the second equation and I'm going to multiply by minus 1. So I can't just multiply the minus 1 times the y. I have to multiply both sides by minus 1. So that is going to give me 2x plus y plus 4z equals 23. So haven't changed equation 1. But equation 2 is now going to become minus 5x minus y minus 2z equals minus 19. If I draw a line underneath it, I'm now going to add the two equations. So 2x minus 5x is minus 3x. Y minus y is 0. 4z minus 2z is plus 2z. And 23 minus 19 is 4. I'm going to now give this new equation a name, so I'm going to call it equation A. And I now have to repeat the process so that I can get a second equation in terms of x and z. So that means I can either choose equation 1 and 3, or I could choose equation 2 and 3. I'm going to choose equation 2 and 3. And if I look at the coefficients of y again, well, it's minus 2y in 3. So this time I need to take equation 2 and I need to make that a plus 2y. So that means this time I'm going to take equation 2 and I'm going to multiply it by 2 on both the left and the right hand side. So 2 times 5x gives me 10x, 2 times y is 2y, 2 times 2z is 4z, and 2 times 19 is 38. So that's equation 2. And equation 3 stays as it is, because now my y's are the same coefficient but opposite in sign. If it wasn't, we would have to then multiply the second equation by a number so that I would make the two coefficients the same but opposite in sign. So again, I'm going to add my like terms. So that means I'm going to add my x's. I'm going to add my y's. I'm going to add my z's. And I'm going to add my constants. And I get another new equation, so I'm going to call that equation B. So basically, equation A and equation B should always have two variables in it, or one, but the variables should be the same. So that means I now am back to simultaneous equations with only two variables. So if we line them up, lining up the x's and lining up the z's, I can now see exactly what I need to do so that I can eliminate a second variable. So I'm going to decide to either eliminate x or to eliminate z. And I'm going to go with the elimination of z. So that means I'm going to have to make the coefficients of z the same but the opposite sign. So this time I have a 2 in front of the z and a 5 in front of the z. So really the easiest way to go is to find the lowest common multiple of 2 and 5. So that would be 10. So that means to make 2z become a 10z, I'm going to have to multiply both sides across by 5. And to make 5z a 10z, I'm going to have to multiply both sides across by 2. But of course, we need to remember that the coefficients have to be the same, but opposite in sign. So that means it has to actually be a minus 2. So that's going to give me minus 15x plus 10z equals 20. And if I multiply b by minus 2, I'm going to get minus 26x minus 10z equals minus 102. So again, if I draw a line underneath the two equations and I add my like terms, well, that gives me minus 15x minus 26x is minus 41x. 10z and minus 10z is 0. 20 minus 102 is minus 82. And now I have one variable on its own equals minus 82. So therefore, to get x on its own, I'm going to divide both sides across by minus 41. So that gives me a value for x. So x is equal to 2. So now I have my first answer. I need to find another variable. So if I look back at the original three equations, they had x, y, and z in it. So if I now know the value for x, I can't sub it into either of these equations 1, 2, or 3, because that would still leave me with two unknowns. So instead I have to focus on the equations a and b, because they only have two variables, one of which we know, x, and therefore if I sub it in x into either a or b, that will leave me with z on its own. So it doesn't matter which equation I choose, a or b, so I'm going to sub x into a. So that becomes minus 3 times x plus 2 times z equals 4. So in other words, minus 6 plus 2z equals 4. If I add 6 to both sides, that gives me 2z equals 10. And if I divide both sides across by 2, well, 10 divided by 2 is 5. So now I have two variables. I have x and I have z. So again, if I go back to all of my equations, 1, 2, 3, a and b are no longer any use to me because I already know x and I know z. So of course, the third variable that I have to find is y. So the only equations with a y in it are equations 1, 2, and 3. And again, it doesn't matter which equation I sub x and z into. So I'm going to sub x and z into equation 1 to finish. So I'm always writing down which equations I'm subbing back into. So if I make a mistake, I can go back and find my mistake. So that's going to be 2 times x plus y plus 4 times z equals 23. So that's 4 plus y plus 20 equals 23. So rearranging to get y on its own, well, that gives me 23 minus 24. And 23 minus 24 is, of course, minus 1. So, of course, what does this represent? Well, we'll have a look back at our 3D plane. So we had our three equations represented by these three different planes, the blue, the yellow and the red. So when we find the solution, a value for x, a value for y and a value for z, what we're actually doing is we're finding the point of intersection of these three planes, which can be seen here as the point A. And of course that point A means that we have gone out 2 on the x-axis, and we have gone out to -1 on the y-axis, and we have gone up to z equals 5 on the z-plane. And therefore this is our point of intersection, or it might look a little bit clearer if I make all of the planes the same colour. And we can see the overlapping of all three planes at exactly 1 point. So that point is generally written, not necessary for the leave insert, but is generally written as a coordinate x, y, z. So we had 2, -1, 5 as our solution. So as I said, we do not read to write it like this in the leave insert. We just write x equals, y equals, and z equals. So let's look at one more example where one of the variables is missing to begin with. So here we have three equations: y minus z equals 3, x minus 2y plus z equals -4, and x plus 2y equals 11. We can see that we don't need to rearrange because all the variables are on the left and all the constants are on the right. So I'm going to number my three equations, 1, 2, and 3. I see that in equation 1, x is missing, but I see in equation 3 that z is missing. So what I need to decide is which variable do I want to eliminate from two equations so that I end up with two equations with the same variable. Now, because I have two equations that are missing two different variables, I can decide to either get rid of x from equation 2 or to get rid of z from equation 2. So I'm going to eliminate x from equation 2, which means that I will need to take equations 2 and 3 together. So that means the coefficients of x have to be the same but the opposite sign. They are currently the same coefficient, so I'm going to multiply equation 2 by -1 so that their signs end up opposite. So that gives me -x plus 2y minus z equals 4, x plus 2y equals 11. So if I line them up and I add my like terms, well, -x plus x is 0, 2y plus 2y is 4y, minus z, and there's no z there, so I'm basically adding 0 to minus z, which just gives me minus z, and then 4 plus 11, which is 15. I call my new equation A. So now, if I look at equation 1, I also have an equation with y and z in it. So this time I don't need to get another equation and call it B. I already have it. So it's less work involved in this type of simultaneous equation. So essentially what I'm doing is I'm taking equation 1, I'm lining it up with equation B, and I'm checking which variable do I want to eliminate next. Do I want to eliminate y or do I want to eliminate z? Z is clearly the obvious one to eliminate because the coefficients are already the same, but the signs are the same. So that means I need to multiply one of my equations by -1. So I'm going to take the equation A and I'm going to multiply it by -1. So that gives me y minus z equals 3, minus 4y plus z equals -15. And now if I draw a line underneath it and add my like terms, my z's are going to cancel to give me 0. Y minus 4y is minus 3y. 3 minus 15 is minus 12. And if I divide both sides across by -3, well, minus 12 divided by -3 gives me the answer 4 for y. Now I have one of my answers for one of my variables. If I look at equation A or equation 1, if I sub in for y, that's going to give me the value for z. So I'm going to sub y into equation 1. So that gives me 4 minus z equals 3. So if I subtract 4 from both sides, I get minus z is equal to -1. And dividing both sides across by -1 gives me z equals 1. So now I have both y and z. So that means I have to sub it into either equation 2 or equation 3, because they both have an x in there. So I'm going to sub y into equation 3. There's less work to do with this because I just have x plus 2 times y. So of course that gives me x plus 8 equals 11, and therefore x equals 3. So again, I could have subbed in for z and y into equation 2, and that would also give me exactly the same answer for x. So that means that our 3 points for x, y and z are x equals 3, z equals 1 and y equals 4. Okay, so let's summarize what we did with this 3-variable simultaneous equation. So we start by rearranging our 3 equations so that the variables are all on the left-hand side and the constants are all on the right-hand side. We then number our equations 1, 2 and 3. We then choose the variable that we want to eliminate and pick 2 equations. So we then multiply each equation by a constant so that the coefficients of the variable that we've chosen is the same but opposite in sign. So we then add these 2 equations, adding the like terms, and the answer we get will be called A. We then repeat the process by taking 2 different equations, but we have to make sure that we are eliminating the same variable, and the new equation that we get we call the equation B. We now have 2 equations A and B, which should have 2 variables in it, and we then basically solve the simultaneous equations as before in type 1, and we will get our first value for one of the variables. Sometimes with the equation A and B, you'll actually end up with solving a value straight away without simultaneous equations. So now that we have found our first variable, we're now going to sub that back into either A or B to find the second variable. And once we now have 2 variables, we simply take both of those variables and sub them back into either equation 1, 2 or 3 to find the third remaining variable. Okay, so let's go to page 31 in Active Maths Book 1, and we're going to do question 5. No, sorry, wrong page. Sorry, that was the 2-variable simultaneous equations. We're going to go to page 32 for our 3-variable simultaneous equations. And we're going to solve question 2, which has 3 variables in each equation. Question 7, which is going to take rearranging our equations, so bringing all the letters to the left and all the numbers to the right. And then question 8, which has fractions in it in the second equation. So again, we're going to have to multiply across by the lowest common denominator to eliminate the fractions before we begin our simultaneous equations.